Transense Technologies has worked with the experts at drive system design to create a new technology that enables higher power density electric motor drive systems. Using drive system design's unique simulation and development expertise and Transense's novel torque sensor technology, the key to unlocking this new approach. So how do we increase electric drive system power density? It may seem obvious, but we need to make the powertrain smaller and lighter. To do this, we need to design systems that operate at higher speeds. Higher speeds mean reduced control algorithm execution times, but there is a limit to algorithm execution speed and therefore a limit on motor speed and power density. Our new approach removes this limit with its faster execution time. Motor control algorithms can be thought of as sequential procedures. You follow a defined set of steps which you can't skip or remove. These steps in turn define the execution time, which in this case for field-oriented control is 8.24 microseconds. The motor speed defines the window in which you must perform these calculations, but the problem is that in the most commonly used approach, field-oriented control, the entire window is taken up. Therefore, you can't make your machine faster and your powertrain smaller than this processing limit allows. The solution is to shorten the execution time. To achieve this, Transense and Drive System Design have used direct torque control, or DTC. Now, for anyone who has used DTC before or is familiar with it, you will know that it suffers from torque ripple error. There is also an interdependency between the observers which only makes the problem worse. The red trace shows the torque response with its large ripple, which sits over the blue torque command. With DTC, you are forcing waveforms onto the motor, but that doesn't necessarily give you the torque that you ask for. You can see this by the green trace, which shows the actual torque, and this is a problem, because it means you don't get the vehicle performance that you want. The ripple and error enter through the use of measured currents in the torque observer which inject noise, and the interdependency with the flux observer, which also has noise injected through the voltage and current measurements used. We can eliminate these noise paths by replacing the torque observer with an actual measured torque. So what does this look like? The red line shows measured torque directly feeding the DTC control, unlike traditional DTC, which needs the torque observer. This new method eliminates the noise paths and interdependence from the torque observer. The result is the delivered torque shown in green is now aligned with the torque command, meaning you are now getting the torque that you asked for. Compare that with the red estimated torque from the torque observer, which doesn't reflect the real torque at all. Torque ripple on the green line has been reduced by 50% through the elimination of the noise paths. All of this leads to significantly improved electric motor performance. But there are challenges to implementing torque sensing in electric motors. Normal torque sensors are commonly used in dyno testing, but they are too big and too costly to be included in a powertrain system. As well as needing maintenance and being susceptible to electromagnetic radiation and DC magnetic fields, measuring output torque in a production motor system is very difficult, and not something that most engineers even consider in the development process due to these issues. Surface acoustic wave, or SAW sensor technology, provides a robust solution for torque measurement in electric motors. A wireless, non-contact system consisting of two main components. SAW sensing elements, passive strain and temperature measurement devices mounted on the rotating shaft with a simple antenna called an RF coupler, and an electronic interrogation unit called a reader connected to its RF coupler. The reader creates an interrogation signal which is transmitted to the rotating shaft through the RF coupler. The SAW sensing elements on the shaft do not require any other power source and work as a passive backscatterer, reflecting the interrogation signal back to the reader. The backscattered signal's frequency of oscillation is affected by the physical measurements such as strain and temperature. The reader analyzes the received backscattered signal and calculates the value of the strain and temperature measured. The shaft surface strain gives us an accurate measurement of shaft torque. In any powertrain design, cost is a critical factor. Any additional component will add to cost. But with this improved direct torque control technology, we can potentially reduce the overall cost of the system. We have removed the requirement for the costly sine-cosine position sensor. Because the algorithm is much simpler to execute, we've been able to reduce the need for processing power. This opens the door to lower cost microcontrollers, which are always going to be a significant part of the control system bill of materials. The world is moving to electric drive in automotive, aerospace, and robotics. These industries are fast-moving, driven by the need for competitive advantage in future powertrain products, and that competitive advantage comes from increased efficiencies. Contact Transense today to learn more about SAWsensing technology and how it can help deliver your competitive advantage.